Alright, recording started.
Hello. We are back at topic 3, which is now circular motion. We went over topic 2 last time when no one showed up. Um, so hopefully you understand dynamics. If you don't, feel free to ask questions at any point.
Yeah.
Anyway, Alan, you want to start?
Uh,
Or do you
yeah.
want me to?
Oh, you guys were just doing this, weren't you? Yeah. You guys were literally just doing circular motion. Okay. So, to start, you got free body diagram of circular motion. So, for your free body diagram, it's going to always be, you have your center, and then there is, assuming the rotation is, I'll just draw like a circle here. You're gonna be like taking a picture here, and you're gonna be diagramming what's going on right there. You're gonna have one force pulling in here, which is going to be your uh, this is like if you have an object on a string, this will be your like your tension force keeping it on. And then for the most part, if it's just circular motion, that's all you're gonna have. It's just that pulling inwards and changing the velocity as it goes around. Uh, I know that the worksheet you guys had, there were some weird ones with the free body diagrams, but that was because it wasn't just simple buck. It wasn't just a simple uh, something on a string being swung around. So
So a question I want to ask, looking at this free body diagram, in uniform circular motion, there's generally speaking only one force. So where is, in the most general case of circular motion, where is the object always accelerating towards? Anyone can tell me.
The center.
Yep, it's always accelerating towards the center, because the net force for rotational circular motion always is pointing towards the center.
okay, so next one, yes, all the analogs. So for most of the centripetal or the circular motion things, like you have your uh, angular displacement, which is represented by theta, which I put there. Theta is the analog to, is it delta theta or just theta for change in x? I don't remember.
I mean, usually you just use theta.
Yeah,
I mean, you can use, it's the same, right? So theta means displacement.
yeah,
Um, so
yeah. So
if you
theta.
look at the way that they do it, they never actually use change in x. They always use x is equal to x naught, blah 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 blah. So they do the same thing. Theta is equal to theta naught.
Okay. Yeah. So you can switch between these using the radius because, of course, theta for the most part is in radians. And if you just take your radians and multiply it by the radius, you'll get it in meters, and vice versa. You take the displacement and divide it by the radius, you'll get it in radians. So then the analog for the angular velocity is just wacky looking. I think it's lowercase omega, right?
Mm-hmm.
Yeah, lowercase omega, and that is the analog for velocity, which is of course is v, and then that is shares the same way with r, or with the radius. So take the angular velocity, multiply it by the radius, and you'll get the velocity in meters per second. And then take the velocity, divide it by the radius, and you'll get the velocity in radians per second. And then there's no, just correct me if I'm wrong, but there's no like there's no acceleration analog, right? You don't deal
Yes,
with that
there
for
is.
circular motion. There is?
Yes, you do.
Oh, what?
It's alpha.
Oh, yeah. None of the problems that they had dealt with this. I had completely forgotten about that.
It's rare, but it is in the AP curriculum.
Yeah,
They could totally do it. They did it on our test, if I remember.
I'm trying to make trying to make it obvious that there's a difference between the alpha and the A. It's a symbol that looks somewhat like that. Uh, it's like it looks more like a circle and then a semicircle than an A. And then that is done, the same way. You just use radius and go between them.
Looks more like that, but whatever.
Like that. It's fine.
All right. So these are all analogs between what we've been dealing with at the beginning for um, linear motion, and this is for rotational motion, which means pretty much all the equations are the same, just with the variables swapped around. So for example, with regular motion, we had like v is equal to at, right? So what would be the analog equation for rotational motion? Anyone? So remember, we just swap out the variables, right? So there's no analog of time. Time just exists. It's the same.
Time is time.
Yeah. Acceleration is going to be angular acceleration, and velocity is going to be angular velocity. So that's just omega is equal to alpha time. Same thing.
Mm-hmm.
So another one, I'm going to move the board a little bit. With linear motion, we had change in x is equal to vt plus 1 half a t squared. So what do you think the rotational analog to that equation is? Anyone can answer.
Did he go over this stuff, or did he just like kind of just not mention it?
I think everyone's dead.
I mean, it's looking like it.
We died.
I think he mentioned it.
Yeah, I think we're all just confused right now.
Oh well, what's confusing? What doesn't make sense?
Just specifically, just so we know what we need to go over.
Yeah.
Can you repeat the question?
Yeah, so earlier we said, so we showed you up here, every single or most of the linear variables for linear motion have analogs for rotational motion, right? Which are essentially variables that mean the same thing under the context of rotational motion. So change in x is change in theta, v is equal to omega, and our acceleration is alpha, right? And so all the equations translate over. So the equation we used in linear is v is equal to at. That translates to omega is equal to alpha t. So the question is, an equation we use in linear motion is change in x is equal to vt plus 1 half at squared. That's one of the first equations on the AP formula sheet. So what is the rotational analog to this equation? If you look at the other example, v is equal to at, which translates to omega is equal to alpha t. All we're doing is swapping out the variables for the rotational analog. So what do you think the analog for that bottom equation is?
To be honest, I forgot what all the names of the letters are.
So
Plus, I don't know. Like, I feel like when I think omega, I do not think of like a W.
So
that's
a
lowercase omega. Yeah, it's lowercase omega.
Oh,
So uppercase
mean-
omega is the omega you normally think of, but that's lowercase omega.
Alright.
So wouldn't it be theta equals angular velocity t plus half of angular acceleration t squared?
Yep, that is correct.
Okay, cool.
Oh
So
my
we
gosh,
would
Sophie
be
is so smart.
change in theta equal to omega t plus 1 half alpha t squared.
Yep.
Okay. And then what's the last one?
Lesson's the weird one, right?
Yeah,
The
actually, I'm not gonna go over that. You barely need to know that, so never
yeah.
mind.
To be
So
fair,
these are the.
yeah.
Go
You
ahead.
don't really use You don't really use angular like this kind of angular acceleration. Like it's if you're seeing it on a test, you're seeing it in this context where it's just analogs.
Mhm. So those are the main equations that you need to know, and in the event you need anything else, it's all analog, so you can just swap out the variables. But the other question is how, if we know, if we have a circle like this, and this object, it's awful. Okay, there we go. And we have an object here, that is going in rotational motion. And it has a radius of 2 meters. I'm not gonna write m though. And at this moment in time, um, its velocity this way is 10 meters per second, right? Because remember, one other thing to remember is that its velocity, its regular velocity at any point, is always going to be tangent to its rotation. So basically, if whatever was holding on, if it was a string, were to just suddenly disappear, it would continue going in a straight line. That's one thing to remember. But going back to this problem, if its regular velocity is 10, how can we calculate its angular velocity? Or just more broadly, how can we convert between the angular variables and the regular linear variables? Any guesses?
Would we divide by the radian?
Close. But
We multiply by the radian?
yeah, for this
Oh.
going between from angular to linear is you multiply by the radius.
No,
Because if you
the question was the other way around.
oh
You were
was
right the
it
first time. This I'm asking the linear velocity is 10.
I'm dumb. Yeah, no, you divide by the radius.
Yep.
Yeah.
And that gives you the angular velocity, and remember that its units is in radians per seconds. Never put degrees, you will get questions wrong.
Yeah.
It's always in radians.
Yeah.
And vice versa. If you knew its so in this case its angular velocity would be 5 radians per second. And if you knew initially its angular velocity was 5 radians per second, then you can multiply by the radius of 2, and you would get its linear velocity of 10.
Yeah, and the easy way to remember this is that the units of angular velocity is radians per second, and 1 radian is just the length of the radius. Like that's why uh for the circumference of the circle it's 2 pi radians, because what that's what that's what that is. It's just that's how it works. It's the radius of the circle. So for moving in between a number that means this many of the radius of the circle and meters, you just multiply to get the meters. You just cancel them out.
Yep. So just key thing to take away there is that 1 radian is always equal to the radius. So
Mhm.
radian is sort of a pseudo unit, if you will. It's not really a unit because it represents whatever it needs to represent in the problem, but we basically treat it like a unit. So similarly again, everything here is analog. So if I say this object traveled in some length of time, I don't know, 0.2 radians. And the radius of the circle is still 2. How can we get its linear displacement? So we know its angular displacement is 0.2 radians. How can we get its its linear displacement?
Multiply by radians.
Yep, you multiply by the radius. So the radius is 2, so you just do 0.2 times 2, and that gives you its linear displacement. And then the last one obviously is acceleration. And technically speaking, yes, if you knew the acceleration, you could sort of figure it out. But that's not what we're going to do in this case, because where is acceleration always pointing when we're doing rotational motion? We talked about this earlier. The linear acceleration. Where is linear acceleration always pointing when an object is in uniform circular motion?
Tangentially.
So that would be the velocity. The velocity is always tangent. Where is it always accelerating towards if it's in rotational motion? Does anyone know?
Towards the center?
Yep, towards the center. And so I'm not sure if I'm going to be able to explain this super well, but I'm going to try here. If you just imagine an object here that is supposed to be in circular motion, right? Between this and the next instant, it will be over here, right? So its velocity was initially here, and now its velocity is like this way, right? So between those two states, it accelerated a little bit towards
You
the
want to put
center,
an anchor point, yeah.
right? Over here. And then, a little bit later, it's now this way, right? And so between these 2 points, it again accelerated towards the center. Over here, now the velocity is this way, and it accelerated towards the center. right? So always it's accelerating towards the center. And even though its speed may not be changing, what's happening is um, since the acceleration, if you notice, every single time, my drawing isn't the best, but every single time, the velocity and the angular acceleration are perpendicular. They're at 90 degrees. Ignore that last image. That last one sucks. But they're always perpendicular. So while it's not technically changing the speed of the linear velocity, it's always making it point more towards the center, which causes it to get in this rotational motion. So the acceleration of any object in uniform circular motion always points towards the center, and likewise the net force always points toward the center, because the net force and acceleration always point in the same direction. So because of that, we can use a simple equation to figure out the linear acceleration at any point, and that is simply v squared over r is equal to linear centripetal acceleration, or the acceleration towards the center. I can't draw when I'm that close to the side. And that is on the AP formula sheet. It's like the 4th or 5th one, I think, or sixth one. And so that is the last equation you need to know. And there's no true analog for that one. But you just have to remember, if we're in uniform circular motion, then v squared over r is going to be the acceleration towards the center of the circle. Any questions so far? Anyone confused?
All right. Are we watching the video from, what is it, 1950s? What are we doing next?
Sure. Frig, I didn't bookmark it. Ah, hang on.
All right. So there's this one video that Mr. Mill showed us from, it was some American association, which it's like it's 1950s, 1960s. It's a super old video, but it does a better job of explaining these kinds of concepts than anything I've ever seen, like besides this. So it's a long video, but did you pick out the parts that you wanted to
You see,
give to?
I thought about doing that, last Thursday. Then I just didn't.
Yeah, fair enough.
All right, hang on. I'm gonna see if I can skim through this and find parts that are important.
We could just watch it at like 1.5 times speed.
No, that's gonna take like 15 minutes.
That's true. Yeah. So the video just goes over the nature of motion in with circular motion, and some of the things, like if you try to put it down on paper in math, it's like impossible to understand, but once you see it happening like in a video or in real life, it makes more sense. And this video does a great job of kind of showcasing those things.
Okay. So, for right now, we're only gonna watch this clip. Later on, I think what we'll do is we'll do the other clips as they're relevant. If you ever want to watch this video in full, which we did, it is beautiful, because it's from 1960. So, but other than that, I'm just gonna pick excerpts. But before I show this one, one thing to understand is about centrifugal force. Obviously, we talked about centripetal force as the force towards the center, right? Centrifugal force is the quote-unquote force that you feel towards the edge of the of whatever you're in rotational motion, and it's not real. It is similar to how when you're in a car and you accelerate forward, you feel pressed backwards, right? You feel like there's a force pressing you back into the car, but that's not what's happening. You're really being pushed forward, right? And so if you've ever been on anything that spins, you normally feel pushed towards the edge of the thing that you're spinning on. But again, that's not what's happening. Really, it's pushing you towards the middle. But because you're rotating with it, it feels like you're getting pushed towards the edge. So I'm gonna show this clip, which may or may not make sense out of context. But let's go. Let's just go with it. And everyone double check that they can hear it when it starts. Oh god.
Ooh, it's quiet. Might just be me, but yeah, I think it might just be me.
That when we see an
Yep.
acceleration of the ball sideways,
This is from an earlier part. Hang on. All right, there.
that there is a force causing it. what's happening this time. Why doesn't the puck move straight across the table as it did before? As you can see, it doesn't. So, if we believe in the law of inertia, then we must believe that there is an unbalanced force to change the velocity of the puck. But this puck is nearly frictionless, so what can be exerting this unbalanced force on it? Suppose that you watch the motion, this time, through a camera which is fixed in the Earth's frame of reference. I think if you concentrate on watching just the puck, you can see that it is moving in a straight line, and that therefore there is no unbalanced force acting on it. Now we're going to stop this rotation so that I can talk to you about what is happening here. I don't know about you, but I'm dizzy. In the Earth fixed frame of reference, there was no unbalanced force, but in the frame of reference rotating in this turntable, there was an unbalanced force because the velocity of this puck kept changing. This was a fictitious force. The rotating frame is a non-inertial or accelerated frame, just as the accelerated frame of the cart that Dr. Hume showed you was. You know that every object which is moving in a circle has an acceleration towards the center of the circle. This is the acceleration that has a special name, the centripetal acceleration. Now you hold this puck for a while, hold it steady, while the turntable is rotating, and I'll get off. Are you ready? I'm ready. Start the rotation. You can see that now the puck is moving in a circle. Dr. Hume is exerting a force to keep it moving in the circle, and you can see this from the fact that the rubber ring is extended. He is exerting the centripetal force, and this is the only horizontal force acting on the puck. But now let's look at it again from his point of view in the rotating system. He is exerting a force towards the center of the table, and yet the puck is standing still, at least more or less still. There is some vibration. Now he believes in the law of inertia, so he thinks there's an equal force on the puck away from the center of the table, so that there is no unbalanced force. This outward force on the puck is the fictitious force in this case. Sometimes it's called the centrifugal force. In the fixed reference frame, there is no outward force on the puck. Now suppose that Dr. Hume stops exerting a force. Watch the puck. In the fixed frame of reference, the puck moves off in a straight line. There is now no unbalanced force acting on it. Now let's look at it again from his point of view in the rotating system. When he releases the puck, which to him was at rest, it moved. The force away from the center is now an unbalanced force on the puck to him. Remember, to us, the outward force on the puck is fictitious, because in our Earth frame of reference it doesn't exist. But to Dr. Hume, in the accelerated frame of reference, it's a perfectly real force.
Okay, I think that's. I don't believe they go into much. Yeah, the rest of it is unimportant for right now. So the important thing to take away from that, because that I will say is, especially with the newer curriculum, is a fairly popular set of questions is to ask about non-inertial reference frames. Um, so the main thing to take away from that is a couple things. One, when you're rotating with it, nothing is the same. There appears to be fictitious forces. And two, that from a regular reference frame, if you let go of something that is rotating or the force that is keeping it in rotation stops existing, then the object goes in a straight line, like we talked about before. Do you have anything else to say?
No, that's it for me. I don't have anything else to add to that.
Okay. So as we get into other parts, we'll come back to other clips of that video. I would, if you have 27 minutes or, 12 minutes if you played at 2 times speed, of free time, I would highly recommend watching the whole thing. But I don't have time for that here. So, yeah.
I have a question actually. How much did you guys talk about gravitation? How much did Dr. Florence say about that?
He talked about it, but I'm not sure what he said specifically.
All right.
Nice.
If we were to write out the equation of universal gravitation, would you guys recognize it?
Probably not.
All right.
At least for me.
Nice.
All right. Well, should we start with that then?
Yeah, that's the next thing on the list, right? Isn't it? Yes.
All right. So,
Okay.
can't you
see.
copy it over?
Well, I forget how, because I've been dealing with IB for like 2 days now, 3 days. I want to figure out. I forget how AP writes it. They write M on them too. Okay. So,
You want to
yeah,
handwrite it or just copy it?
I'm just gonna handwrite it. So,
Alright.
of the force due to gravity is equal to the gravitational constant times the first mass times the second mass all over the distance between those two masses squared. And G is equal to, and this will pretty much always be given on the test, otherwise it's on the formula sheet. G is equal to 6.67 times 10 to the negative 11th. So yeah, what this equation talks about is how to figure out the gravitational force between two large masses, like planets and such.
So I'm sure at least some of you are thinking, well, why would you have the equation for gravitation in the circular motion section? Those don't seem very connected. But the thing is that all of the orbits that our planets are in are basically just big circular motion problems, with the centripetal force being the force of gravity from the sun.
Mm-hmm.
So.
And so how you can connect this is like if they give you, two planets and their masses and their distance, right? And they ask you to find the force, right? So you can plug your masses and your distance. Remember, r in this case is distance with your gravitational constant, and get the force, the attractive force between the planets. But if you know one of the planet's mass, you can get the acceleration, right? Because F is equal to ma. And if you get the acceleration, then you can get the linear velocity of the planet because v squared over r is equal to a. And so then now you're back into the rotational motion world. So it is, again, extremely popular set of questions for them to combine rotational motion and gravitation. Usually in an FRQ, to be quite honest. Happens almost every year, at least from what I've seen. So in general, are there any questions about what this equation means or where you would use it?
Could you explain maybe the terms of it? Just like describe the terms.
Yep. So this is the gravitational field constant, or what do they call it? Universal gravitational constant. So these ones over here, m1, and m2, those are the masses of the two objects you're dealing with. Obviously, it doesn't matter which is which because they're just multiplied together. And then r is the distance between the two.
It's specifically the distance between the center of both.
So the radius.
Yeah, if you think about it in terms of like an orbit.
So,
Okay.
like, if I said, I have Earth and its moon, and I'm gonna make numbers that don't make any sense, just letting you know. Let's say that it was 100 meters apart, and Earth's mass was 300 kilograms, and the moon's mass was 10 kilograms.
This will be
Right?
a
Obviously, this is ridiculous. Okay, don't take away. These are numbers that make sense.
no, you're gonna get a
Um,
super small force.
But what you would do is you would take, okay, if we want to find the attractive force due to gravity between these two, you would do the mass of Earth, which is 300. Remember, always in standard units, so kilograms and meters, right? Times the mass of the moon, which is 10, over the radius squared, which would be 100 squared. And then multiply that by the gravitational constant, which is 6.67 times 10 to the negative 11th. And you would get approximately 2 times 10 to the negative 11th newtons. So that's how, if you're given, two masses and a distance between them, how you can calculate the force between them.
Okay.
So the other places can be applied is, somewhere over here. Actually, I'm going to move it. I'll write this down over here. So we have a planet that is, again, is our 300 kilograms. And I, as a person, am standing 100 meters away from the center of the planet, right? What I would want to know is what acceleration do I feel due to gravity, right? But if we look, and in this problem, I'm not giving the mass of the person, right? So knowing what we have earlier, this is a bit of a tough one. But I'll see if anyone can figure it out. Using this equation we have up here, which is gm1m2 over r squared, how could we figure out the gravitational acceleration of a person in this scenario, even though they didn't give us the mass of the person? So if we were to hypothetically get the mass, or let's say we had the mass and we were able to get the force, what would we do to get the acceleration if we had the force?
Divide the mass. Or divide the mass, yeah.
Yep. So if we knew the force and we knew the mass of the person, we could divide. So let's say that this planet over here is mass 1 and the person over here is mass 2. So then we could take, if we knew the force, we could say that the force, I'm going to move it up, the force over the mass of the person is equal to the acceleration, right? So if we put that back into our whole equation, so force over mass of the person is equal to gm1 m2 over r squared mass of the person. So all I did here was I divided both sides by the mass of the person, right? Let me write that in. Now, these two cancel out, right? And so what you're left with is gravitational acceleration is equal to the constant times the mass of the planet over r squared. Which, if you think about it, makes sense, right? All of us on Earth are accelerating at 9.8 meters per second. It does not matter what our mass is, right? So you don't need the mass of an object to figure out its gravitational acceleration due to another object.
How did you get f over m2? Because you said could you scroll slightly left?
Yeah. Hang on.
You said f equals to that. So how I get that f equals f over m over 2 is equal to the acceleration.
Right. So all I did between these two equations over here is I divided both sides by m2. So I just divided this side by m2 and this side of the equation by m2. And since both sides are being divided by m2, they're still equal. Just like in algebra, if you divide both sides of the equation by the same number, the equation's still equal, right?
Mm-hmm.
So all I did was I just divided both sides by m2, and then on this side, this m2 cancels out.
Okay.
Does that make
So
sense?
essentially, you get acceleration equals. Oh, okay.
Yeah.
Yeah. So you get acceleration is equal to the mass of the body r squared. What were you gonna say, Alan?
Yeah, I was gonna say use F equals ma to set the force divided by the mass equal to acceleration, and then you just cancel out on the right side, and then you're left with g m1 over r squared. Oh,
Is anyone can
can you
go
post
ahead?
the link to the video from MIT in AP homework help?
Yep. Um, is anyone confused by how these two equations work together?
I hope by now, Dr. Ivy
The
and I
G is the gravitational force, correct?
G is the universal gravitational constant.
Big
It's
G.
always
Yeah.
equal to 6.67 times 10 to the negative 11th. It is on the very top of the AP formula sheet.
Okay. Probably a dumb question, but what is the universal thing?
It's
It's just a constant.
it's like
Oh.
it's a made up number made by Isaac Newton to make this equation work, basically.
Oh. So, like, it represents.
It's technically it like represents the relationship between strength of gravity and mass, the strength of gravity compared to mass and radius, but like god, that's gonna get in a whole big physics talk, but like all of the equations and stuff we use are approximations of how the real world works, and the use of this equation works well in 99% of scenarios, but whenever you have the extremes, like if you have, for example, a really, really, really high acceleration due to gravity, that's when you start getting into like relativity. And you start getting into Einstein because at that point your accelerations are so high that you're experiencing time dilation, and that adds a whole bunch of whack stuff. And you're not in IB, so you won't ever have to think about that because it hurt brain. It's not fun. But yeah, so this is essentially it's just an approximation to make it work in most scenarios, and that's why
Yeah.
that's the numbers what it is.
I mean, so like there is something it represents, but it's not gonna make sense.
Yeah.
Like the unit, for example, is m cubed over kilogram second squared, and if you know where that comes from, it has to do with like the area of orbiting planets is the same no matter where they are, and this whole giant thing we can get into if you want to later. What like after the meeting, I can get into it. But as far as what you're gonna need to know for AP and IB for that matter is it's a number that makes it work. It doesn't really represent anything in particular.
Mm-hmm.
Okay.
Okay. Is there anyone else who has questions about this? Okay. And then the last piece to this, actually, we kind of already went over that. Alan, what did you mean by this last point above the question? I'm confused there.
That's just the equation for uh what's it called? That's just the centripetal thing.
Centripetal force.
Yeah.
Okay. Well, I'll just write it. So, last piece, this is sort of not related to what we were just talking about. Well, it is a little bit, but earlier we said, remember, v squared over r is equal to the centripetal acceleration. So if you ever need the centripetal force, excuse my F there, all you need to do is m v squared over r. Because remember, mass times acceleration is equal to the net force.
Mm-hmm.
Okay. So we're gonna do questions. Is there anything else we have to do before that, Alan?
I don't think so.
Okay. So these first two questions are going to be qualitative questions, which again is very similar to the types of multiple choice questions you will get on the AP exam. I know that on his test. I mean, I don't know for sure, but I'm assuming on his test, most of his questions are like just number based, and almost all the answers are numbers. Is that correct? Or am I wrong in that?
Yeah,
Uh,
on this test there's usually one. There's one like essay response question, and then everything else is just
Okay. So let's look at this first question. This is going to be a question that is very similar to what you would find on an AP test. Alan, if you could drop the link, it's pinned in our session finding channel.
okay. I'm gonna just drop like the. Hold on.
Just drop the PolyV link.
Play V link. Okay. Is it the same Poly V link that we've been using?
It should be.
Okay. Then I'll put that in general.
So we haven't gone over specifically how to do this kind of question. I'm aware. But try and think about it for a little bit and just pick the answer that you think is most logical, and then we'll go over it. The link is in general. How many people do we have, Alan?
Total. Let me look. Total, we have 6, and then you and I.
Okay. Are we still doing the half people, 1 minute left policy?
Sure.
Okay. So yeah, once half the people have answered, which is now, there'll be a minute left to answer. All right, just make a random guess if you don't know.
Are you timing it, Nathan?
I'm just kind of looking at the clock and seeing when the number changes. But you can, on the next one, you do it, please.
Right. We can do that.
All right, we have 6. We'll lock it in. All right, so greater. So anyone who got greater, not just by thinking about the numbers, like by actually, who has a way to figure this out for any set of numbers. Does anyone want to explain how they did it? Okay. So let me switch back to the screen. All right. So earlier we went over the equation for getting gravitational acceleration. Does anyone remember what that is?
A equals G times M1 over R.
Yep.
Or
Over R squared.
okay.
Yep. So, imagine that, and I'm actually going to erase the G here just so it's a little bit clearer. So imagine that this equation represents the acceleration on Earth, right? Because the final question is asking how does the surface of Jupiter compare to the surface of Earth, right? So next we're going to do the same thing, but plugging in what they give us for what the adjustments Jupiter has. So it says its mass is approximately 300 times greater, so it would be 300 m1, and it has a radius about 11 times greater, so 11 r squared. Now this part that's in the squared, we need to simplify that. So what is 11 squared? Anyone? Okay. So 121, 300 m1 is equal to A.
2.4793.
11 squared is 120. Oh, you just do 300 over 121. Is that what you did?
Yeah.
What's that number? Okay, yeah. Over 121. So when we simplify this down over here, in order for both sides to be equal, we need to bring that over to the A side. And so like you just said, that means that A is 2.4799A. And that makes both, I mean, minus the rounding, makes both of these sides of the equations equal. So that means the acceleration on Jupiter is about 2.479 times greater than it is on Earth. And since the answers are only greater, less, or about the same, the answer is greater. Is there anyone who's confused by that?
You're solving for G, correct?
Solving for A. G, you know. The big G is 6.67 times 10 to the negative
Yeah,
11.
this is like the A here is equivalent to like little g.
Oh, yeah,
Okay.
little g, yes. If that's what you meant, then yes. Usually when you're doing this equation, you write A because little g and then big G in the same equation makes for fun times. And I believe the way that they write it, actually, I don't even think they have this formula on the AP formula sheet, to be honest. Let me double check that. No, they don't. So you're just expected to find it from the GM1 M2 over R squared. But anyway, is there anyone any questions about this one before we move on? Okay. So this is a very similar question. It just has numbers as in the answer. Sorry, I'm gonna have to do this real quick. Do we still have 6 or do we have 5 now?
We have 5 now. Alright, I'm gonna start the timer. 1 minute warning. Alright. That's that.
Okay, I'm gonna give 1 second because no one answered in the 1 minute.
Yeah.
Just guess at this point.
Yeah.
Just guess none of the above if you have no clue.
Yeah.
All right, going once, going twice. All right. So the correct answer is 4.9 meters per second squared. And it is very, very similar to the last one. So I'm going to switch back to the board. So like we said, and this one's asking for gravitational fields. So again, we have A is equal to gm over r squared. And it said that the mass was twice as great, so that would be g2m. And then the radius, or the planet's radius was twice as large as well, so that's 2r squared. And remember that this part here needs to be simplified. So 2 squared is going to be 4. So we would say g2 over 4m1 r squared is equal to a. And then obviously, 2 over 4 is 1/2. So that ends up, in order to balance the equation, a has to be 1/2. And, on Earth it's 9.8. So 1/2 of 9.8 is 4.9.
Anyone have any questions? That makes sense to everyone?
Yeah.
See,
Okay.
All right.
Yes, this is a written one, but the answers are just numbers. So for the first one, you just have to know a little bit about a circle, right? How many radians are in one circumference of a circle? Can anyone tell me?
2 pi.
Yes. Right, Alan? I'm not stupid. It's 2 pi.
Yeah, it's 2 pi
Pi.
radians.
Okay, yes, 2 pi. So there are 2 pi radians in one circumference of the circle. So you just have to know that for part A. And rev over s is revolutions per second, just to clarify.
Yeah.
So for the second one, by the way, you have to think about the analogs a little bit, right? We know that we talked about v squared over r is equal to centripetal acceleration, but obviously in this question, unless you want to jump through a lot of hoops, you're not going to know the linear velocity. But you can substitute, excuse me, you can substitute parts of that equation with the analogs to figure it out. All right, we have 3 now, so.
Yeah, timer's been started. Just kind of treat it like a quiz where it's, you don't want to, if you're running out of time, you don't want to just guess every single answer, but if you're getting close, then might as well. Just because it gives us a good idea of how good people have gotten the material and that kind of stuff. Right, that's 1 minute.
All right. Nice.
All right.
Okay, so the bottom one is technically correct. On a test, they probably want you to, because it, would be the multiple choice grid thing. You probably want to put in, multiply 10 by pi, so that should be 31.4. And then the one above that is correct for part B, 118 meters per second.
Those are meters per second squared, but
Oh, correct, meters per second squared. Okay, so let's go over how we do this one, and then that will be it for today, because it is 7:31. All right. So, the first part of the question said that they spin at 5 revolutions per second, and it asks for what is their angular velocity, right? And so the hint I gave was talking about, what is the circumference of a circle relative to radians, and it's 2 pi, right? So if they're going 5 times around the circle per second, they are also going 2 pi radians around the circle per second, or 2 pi times 5 radians around the circle per second. Because every time they go around the circle once, they're going 2 pi radians around the circle. So that just ends up being 5 times 2 pi, and that gets you 31.4 radians per second. Anyone confused by that one? Okay. So the other one asks, what is the centripetal acceleration? And like we talked about in the past, we said a is equal to v squared over r. But we don't know the linear velocity, so we need to use our analogs in order to make this equation into something that we know. And so if we had, from velocity, what can we do to get the angular velocity? If we had a linear velocity. And remember from the very beginning, what do we do to linear velocity to get the angular velocity? Or omega? Okay, well, if you remember, it's you divide by the radius. So v over r is equal to omega, which means that v is equal to omega r. All I did was multiply both sides by r there. And so then we can take this and substitute that in for v. So we would say a is equal to omega r squared over r, and that's just omega squared r squared over r. And finally, if you cancel out the r's, that means a is equal to omega squared r. Any questions about how I got to that point? Okay. And then you know the angular velocity. You know that the angular velocity was 31.4 from the previous question. And you know the radius because it's given, which is 0.12 meters. So you just figure that, multiply that out. So that is 31.4 squared times 0.12. And that gives you 118.3, which is the answer for the angular acceleration. Okay, are there any questions about this question as a whole? Please ask if you have anything. Okay, well, that's it for today, right, Alan?
Yeah, that's it for today. We'll probably do a couple more practice problems next time on Thursday, and then I don't know. I feel like we'll probably be able to move into topic 4, right? I can't imagine these
That
problems
is
will
the
take that
hope.
long.
So again, if you guys have, and I assume you guys, I heard this is what you guys are working on now, or maybe finishing up. I'm not sure, but that's good that we're finally in line with what you guys are doing. So yeah, remember if you have any questions, please let us know. The questions that you just asked are very representative of what you will see on the AP exam. So.
Yeah.
Okay. If there's no other questions, then
So we've covered everything that we've done in class, like throughout these sessions.
I don't think we covered like if he's jumped ahead, like if he's covered.
well,
I know he
but the
covered.
units he jumped ahead to, they removed, didn't they?
They removed waves. I know that. Uh,
We wasted so much time on those, but I guess whatever, it's fine.
yeah.
I'm pretty sure everything he jumped to, they removed, if I remember correctly. Let me check.
I think so.
And I think we're gonna have. He said we're gonna have a review from March onwards, so maybe then, or I'm not sure if we should do review then too, or
Yeah. So, you guys didn't go over torque. You guys, well, I guess you guys did simple harmonic motion. So that's kind of with waves. So technically, we haven't gone over simple harmonic motion yet. Um, but for the rest of it, I think we are at mostly the same place. But we are actually trying. I say trying because we're already behind, but we're trying to go by the pacing guide that AP released for classes during COVID, which is here. I'll put it in there if anyone's curious. I'll put it in general chat, and that has us ending on that one has us ending early April. So we will probably try to end up earlier than that, to be honest. But that is that's the guide that they gave.
yeah.
But we can always do review outside of the regular sessions whenever if you guys need it. But
Mhm.
we'll sort of figure out as we get closer.
Oh no, he's already
Alright.
done energy too.
Yeah, we did energy,
Okay. All right. Well, that's good. Well,
and we did
hopefully
momentum as
then.
well.
Okay. So hopefully then when we get to those units, the hope is that the understanding is there. But the things that we are going to start doing with this unit as well is we're going to start doing the FRQs and eventually experimental design questions because those, I mean, that's worth half the test. So
Yeah.
you might be good at multiple choice, but you may not be bad at those questions or vice versa. And that can either save you or destroy you. So we are definitely going to start practicing those. And I know that's going to be annoying, but trust me, it will make you pass the test.
Yeah.
Has he done? I know you guys. He said he did essay questions. Has he done any experimental design questions?
I don't even know what those are.
All right, probably not. And
Yeah, I don't think he did that.
Alan, have you seen any of the essay questions they've done? Are they like FRQs or no?
They're kinda like FRQs. They don't really follow exactly the same structure, but
Okay. So we're still trying to get access to. By the way, if anyone wants to go, you can go. I'm not trying to hold you back. But we're still trying to get access to Albert.io. We were going to, and then Miss Driblin left, and then it's all chaos at the school at the moment. But we're still trying. I think it's pretty likely. But if not, we may have to make our own. But we'll we'll do what we can. But if we do get Albert.io, Albert.io is both annoying but also great at the same time. But anyway, that's that.
Yeah, Albert.io is like a big question bank for anything you could imagine for AP classes. The school has free subscriptions to I think all of the classes we take, and typically the teacher gives you like the class that you participate in. That's like probably soon, if you have camp, or I don't think Contreras did it, did she? I don't think they have a whole bunch of stuff for English, but for your AP classes, your teachers are probably getting you to join Albert classes at least sometime soon. And it'll trust me, it'll feel like hell, but it prepares you really, really well for the exam.
Oh, I think Camp made us join that in the beginning of the year. I remember something like that.
Yeah. You'll probably start seeing assignments on there more as you approach the test.
That's great.
Yeah. But anyway, yeah, our goal is definitely to be done. Our goal is to be done at least a month before the test. But if that doesn't look like it's gonna happen, we will just slap in review sessions in between regular sessions. But anyway, I have homework to do, so I gotta go.
Yeah, same
but,
here.
If there's anything else, let us know before we go.